now I get to step down off my soapbox, right? And I get to introduce people for the rest of the day, which is terrific. Makes me really happy. And I think I have a little bit of a different energy level than Andreas Tiziolis, who was probably up all night finishing his presentation, as any of us who do these things know. All right, and today I have the distinct privilege of introducing Ralph McNutt. And Ralph and I interacted a couple times during the making of this staging of this event, and I got to watch a lot of his videos online. I recommend them. Google Ralph McNutt and see for yourself. We're in for a treat today, and I'm going to read his bio. Pardon me if I. Dr. McNutt is the chief scientist in the space department at the Johns Hopkins University Applied Physics Laboratory, which he joined in 1992. As project scientist for the Messenger mission, he serves as the principal investigator's right-hand man in making sure that the spacecraft, mission design, and experimental plan answer all 6 of the major science questions the project will investigate at the innermost planet. He will participate in analysis of Mercury's surface composition using data from Messenger's X-ray spectrometer, and gamma-ray and neutron spectrometer instruments. Dr. McNutt is also co-investigator on NASA's New Horizons, Pluto Kuiper belt? Kuiper, thank you. Reading and saying is 2 different things. Mission. Now that was a huge success this year for space. I mean, this shows how people are, we feed it, they eat it. We bring it to them and they'll take it. Our job. Science team member of 2 Voyager investigations. He has been involved in a range of space physics research projects, mission studies, including studies of the magnetospheres of the outer planets, the interaction of the solar wind with the interstellar medium, solar neutrinos, solar probe, interstellar probe missions for the future. Without further ado, Dr. Ralph McNutt.
How do I run this thing?
Yeah, right? Yeah. Teamwork makes the dream work.
Yeah, it also helps because I only speak Macintosh.
What's the magic control key here, Jeff? What is it?
There we go.
And then we don't have a control, so it's
That's all right. I can push the buttons.
Thank you.
Well, Mike, thank you so much for the introduction. I'd like to thank the organizers for actually asking me to come here, and because of the references for about some of the issues about building for the future, I'm going to give you a little bit of a prequel here. I just got back from a joint meeting of the first science working group for Solar Probe Plus and Solar Orbiter, which was being held in Florence, Italy. So I'm a little jet lagged. I was in Florence 36 hours ago. That particular mission is now on schedule. We're going to be launching Solar Probe Plus in 2018. Launch window opens on the 31st of July. So it turns out that this idea of scientifically trying to get down into the corona of the sun is something that has been around since one of the first meetings of the Science Study Board, which was set up before NASA existed. John Simpson was the chair, and that was in 1958. And so almost 60 years to the month, we're going to actually finally be launching that mission, and this is going to be real. It's about $1.5 billion. It's financed by NASA. We've got a variety of people from all over the world that are involved with that, and also with the Solar Orbiter mission, which is going to be going with ESA. So, again, I think it very much speaks to the case that what we do today is writing the history that people will look back on in the future, and you have to hang on to that, because trying to do these things really do take a long amount of time. And it also occurred to me when I was trying to put this talk together, and I've got too many view graphs in here, so I'm probably going to have to pick up some speed. But this itself is an incredibly important date. I think in general, but also especially for this organization. So Turns out at about exactly this time, 38 years ago, as a graduate student, I was down at Cape Canaveral Air Force Station watching Voyager 1 lift off. It's 38 years ago today. Currently, we're at 135 AU. That works out to 18 light hours. We still get about 160 bits per second of data from the spacecraft, typically in about 5 passes a week. And we're still learning things about the interstellar medium. And so what I wanted to talk about today is the fact that we're looking at trying to take the next step past Voyager. So this is a very much talking about keeping your feet on the ground, but what that we can realistically do over the next decade or so. And I want to walk you through a little bit of that, and also talk a little bit about New Horizons, which again has been, as Mike was saying, incredibly successful and is basically still ongoing. So I'm not going to be talking about interstellar travel. I know that that's sort of the main subject here, but it's been talked about for a long time, going back to Robert Goddard, of course, and to others. I'm not going to be talking about colonization, another subject that, of course, people have been talking about over the years as well. But what this is all about, and I do want to talk about, is the new frontier in deep space exploration, which really is the interstellar medium itself. This whole concept of trying to understand how that our solar system interacts with the interstellar medium actually dates back to 1955, it turns out, when at the time we understood that there was certainly a magnetic field of the sun that was associated with somehow modulating cosmic rays that were coming into the Earth. Leverett Davis at Caltech had talked about that and written about that in Phys Rev in 54 and 55. By the time that the early 70s came around, there was this whole idea of what the heliosphere looked like, and indeed that term was invented by Alex Dessler in trying to understand how that the solar wind, which we then knew existed from the experimental measurements from Mariner 2 back in 1962, somehow had to be out there. There was a meeting that was actually held in Seattle, Washington in 1971. This was going along at the same time that the Pioneer 10 and 11 probes were being developed to be the first probes outside of the asteroid belt. And the idea of the scientific and technical bases for solar system escape missions were discussed for the first time at a technical congress. And the idea there, again, was, well, if we can certainly build Pioneer 10 and 11 to get out to Jupiter and to get out to Saturn, we ought to be able to build something to get out to the interstellar medium itself. And there was so little known that it was seen as being something that was a worthwhile scientific undertaking. By the mid-1970s, there was a science formulation that had gotten started on all this. There was a study called The Outlook for Space. It was prepared for then NASA Administrator James Fletcher, which he had asked for NASA to get together. This was people at all the NASA centers spent a year working on this to try to think through what NASA should be doing from 1975 to 2000, the last quarter of the century. A modest interstellar probe mission was in there. By 1976, there had been a mission that had been discussed as an interstellar precursor mission at JPL. That was written up again, looking at the science, looking at realistically what could be done with then technology. In other words, what people were interested in was not what that you perhaps could do with technology that was simply beyond the horizon, but if I took the technology that currently exists and I push on it a little bit, what new breakthroughs and what paradigm shifts can I actually bring about? And that was the idea. And this kind of stuck. So this idea of what then became known as Interstellar Probe, it's been advocated by the science community for almost 45 years now. It's shown up in a variety of NASA reports. It's shown up in a variety of National Academy studies. That is all still ongoing. Most recently, the Keck Institute of Space Studies out at Caltech had a couple of workshops. These were held in September of 2014, in January of 2015. 32 participants. I was lucky enough to be invited to be there. There was a final report due out in July 2015, which does not exist yet, and I'm going to have a little talk with some of the members of the study because they need to kind of get their homework done. The study leads were Ed Stone, course, has been the Voyager project scientist going back from before the launch. Ed's actually going to be celebrating his 80th birthday next year, and Ed is still going strong, as are the Voyagers. In the middle is Leon Alkali, who's one of the engineering fellows out at JPL, and then of course the other person here is Lou Friedman, who is one of the founders of the Planetary Society, along with Bruce Murray at JPL and with Carl Sagan. And this is just the study team. We had a series of very good interactions, and again, this is something we need to actually get out to the public and get that report finished. We had several goals for the workshop. Part of this was trying to figure out how fast that we could actually get out to the interstellar medium. Are we talking about perhaps could we get there in 10 to 15 years rather than what has been accomplished with Voyager? What sort of solar system escape speeds could we get up to? And what kind of a power an autonomous probe could be built that could last for 50 years? Now, you might say, well, Voyager's been out there for 38, that shouldn't be a problem. But it turns out it is a big problem if I'm dealing with the realities right now of getting the government to fund these things. Because originally the Voyagers were to be launched on the Grand Tour trajectory, which was the idea of using gravity-assisted all the outer planets to be able to get up to Neptune in 12 years. People said, oh my God, it's going to be hard to be able to guarantee before launch as a requirement that I can have a spacecraft that will work for 12 years. JPL put together a proposal for how to do that. They had something like 5 different computers on board that had to have some sort of a voting priority in order to be able to assure mission success. Price tag came out at $1 billion in 1970 when $1 billion was a lot of money. And the Congress said, no way, guys, go back to the drawing board, bring the price tag down, and we'll rethink it. And so what happened was a more modest Mariner Jupiter-Saturn program was proposed, which had a mission requirement of being able to operate for 5 years, which would enable you to get to Jupiter and Saturn. And I remember quite well in the mid-'80s, before that Voyager 2 had actually gotten out to Uranus, that the NASA deputy administrator, who was looking for money at the time, said, okay, you fulfilled your mission success criteria, we're going to shut them off. And there was about a 2-year fight that went on where the Voyagers nearly were just literally shut down in the mid-1980s. And all of the science that's accrued since then, including everything the human race knows about Uranus and Neptune, or at least 99.9% of that, never would have happened. So it's an interesting problem how you keep these things running for a long time. Again, with respect to the heliosphere, the interaction of the solar wind with the interstellar medium, we've got a lot of new questions. One of the things, of course, that's been going on more recently is the Interstellar Boundary Explorer mission, which is an energetic neutral atom sensing couple of cameras that are on board a spacecraft in Earth orbit. We've been looking out at the so-called ribbon that is this interaction region between the interstellar medium and between the outgoing solar wind. We actually see energetic neutral atoms that are produced by charge exchange propagating back into the interstellar system. We see them at the Earth. It's again revealing of what's going on with this interaction out there, but as is done with all good science, it's actually raised more questions than it's answered. So one of the things that was done at the workshop was to try to look at this case. We all concluded, perhaps not surprisingly, that there was a lot that you could do, and that there really is compelling science that one could do not only in the interstellar medium, but on the way. There are things that we still don't understand about the zodiacal light, things about solar wind science. There are things that one can do with parallax. A lot of these things really relating back to trying to understand better about exoplanets and their environments as we're looking out and seeing those with Kepler and other assets. The local interstellar medium itself, of course, outside of 50 AU in terms of all of its structures we've discovered with the Voyagers. There's the pristine interstellar medium at a greater than 200 AU, we think, and the question of exactly what's going on with the interstellar magnetic field, with the low energy cosmic rays, other things that might or might not be out there, dust, for example, and again, this is something that feeds back into what we might be seeing with exoplanets. And so a lot of stuff that potentially can be done. And again, from the interstellar medium at greater than 50 AU, there are things that people talked about with gravitational lens focus, and also exoplanets and KBO detection and the detection, sorry, and other things that one might be able to do. Kuiper Belt, the KBOs, the Kuiper Belt objects, we've now known about these since the early 1990s. They've been characterized as the third part of the solar system. And of course, one of the things that we finally figured out was that Pluto really is the sort of the archetype of this other part of the solar system that we really did not know existed. One of the main reasons for flying New Horizons was to try to get an eye onto what was going on with these other objects out there. And it turns out that if I actually build an Interstellar Probe mission to do a fast flyby out of the solar system, I can go out by way of Quasar, which is one of the large Kuiper Belt objects. And people have kind of talked about, well, you know, maybe these things are featureless, maybe you're not going to see a lot. But of course, what happened with New Horizons this last July is we have found out that we've just really started to begin to look at what these things look like. We had, of course, this incredible, well, let's see, 14 July 2015. Sorry, I didn't get much sleep last night. But it was after 9.5 years of flight. We launched in January of, back in January of 2006. There we go. Really didn't have enough sleep. We're now in an intensive downlink phase. This is, of course, the picture of Pluto, the larger one, and Charon, its large moon. For 16 months, we're going to be playing back all of the detailed data from the spacecraft. And there's really been more there than people had imagined. But, you know, that's what you get from discovery, and that's what you get from exploration. The ALICE instrument did UV stellar sun occultation. Looking back, we've been able to better characterize the atmosphere that's coming off of Pluto, and it really is there. The figure on the right, these are all off the public website, shows the haze layer of the atmosphere of Pluto, which we were able to see again looking back toward the sun after closest approach. And of course, it's anything but dull. We've got mountains, we've got nitrogen glaciers, we've got fields of methane, there are fields of carbon monoxide. And again, we're still putting this all together with the more detailed data that's currently coming down and will be for over the next year. We're getting increasing resolution. Most of the images that have come down so far have been at a relatively low resolution. On the left-hand side are mountains that are about 100. This is at a resolution of about 400 meters. That field of view, well, the little yellow bar is about 50 miles across, and there's resolution at 70 meters that's on the spacecraft of all the lit side of Pluto that's still on the spacecraft. That will be coming down. We've got color images of Charon, and again, Charon is anything but a featureless ice ball. And so the idea of actually going by Quasar and being able to see another example of this out there is getting to be not only more and more intriguing, but perhaps more and more scientifically compelling. At least I'd like to think so. And then, of course, this is Pluto. This is our current best Lori high-resolution image of Pluto with the Ralph instrument enhanced color. And again, there's a lot that can be picked out. It's just simply not a boring ice ball. There are various fields. It looks like there's seasonal effects because some of the terrain is cratered. Some of it's relatively craterless, which means that there have been things going on over the last several billion years that have really changed around what we're looking at. It's not over yet. NASA just released a statement saying that we're now going to target for an additional flyby of a small Kuiper Belt object. That flyby will be in January 2019. Thereabouts, the rocket firings have to take place in October of this year in order to line that up. We have enough fuel to reach this when we need to put in about 60 meters a second of delta V perpendicular to the current flight vector of New Horizons, which is, of course, moving now at about 14 kilometers a second. PT1, potential target 1, is about the same size as the two small Pluto moons, Nix and Hydra, and those best pictures are shown down at the bottom left. So we're hoping to get in closer on this one and be able to take some close-ups of that. It looked easy, after New Horizons phoned home. This is a picture that was taken in Mission Ops at APL right at the moment that we got the signal coming back. The spacecraft had indeed survived, coming through the Pluto system, no dust grains that took us out. So again, with that sort of as a backdrop, one of the things that's been going on for a long number of years is trying to figure out how that we put together a payload to go along with the science that one could do with an interstellar probe. This dates back to a study that NASA did back in the year 2000. The real trick on all of this is I need to get a probe. I want it to go fast so that I can get there rapidly. E is equal to 1/2 mv squared. If I want V to be big, M's got to be small. So people have talked about masses for the entire payload of maybe around 25 kilograms and maybe 25 watts, and very, very slow, very, very small bit rates, because again, you've got to worry about the link of getting the data down. We've worked out science traceability matrices. We've worked out looking at the new paradigm of CubeSats. Are there things in CubeSats about what one would do with instruments that might be revealing about what we should be doing on making instruments smaller? Again, you can make comparisons between what's going on now and what people talked about in 1999. It turns out all the masses are things that you would like to get down to. Currently, the instruments that one can build, things that are flying, are about 5 to 10 times too massive. And so there needs to be more thought given to miniaturization. That's something that's been going on, but it's sort of been going on not as really a mainline feature of where the investments have been. And we're going to have to do some more pushing on that before that we can get this off. We've looked, people again have looked at a lot of the requirements and the resources, and there's a lot of real technical challenges in doing that. Of course, the biggest problem is distance. People right now within NASA and people in the science community would like to get out to 200 astronomical units. We think that gets us clear of the, actually clear of the interaction between the solar wind and the interstellar medium. I need to do gravity assist. Basically, if I'm trying to launch something really, really rapidly from the Earth, that maybe I can get up to C3s of between 200 and 350, compared with about the 154 for Pluto's launch. It's still going to take me something between 25 and 30 years, including a Jupiter gravity assist, to get out there. But nonetheless, this is actually doable. Right now, Voyager 1 is the fastest object leaving the solar system. That's because of the Jupiter and Saturn gravity assist. So New Horizons was the fastest launch, but Voyager 1 is the fastest thing moving out. Right now, New Horizons is going to slow down to an asymptotic speed of around 13 kilometers a second. Voyager 1 is at about 16.6. That translates into about 3.6 astronomical units per year that we're moving out. If I do a really, really large launch from the Earth, I can get up to something like around maybe as high as about 8 AU per year for a final flyout speed. And again, while that's not as high as people would like necessarily, it does get me out to 200 AU in something like 30 years or less. And then the trick is, how do I end up putting together a spacecraft that's small enough that I can also guarantee as a mission requirement up front that it will actually last for that 30 years. There's been a lot of examples of this. Pluto New Horizons is about 478 kilograms, Ulysses about 366. The Pioneer 10 and 11 probes about 252, so we can build small things, put them on big launch stacks, and make them go fast. We've done it before. We've looked at various models of interstellar probes. It's the same thing basically that ends up looking a lot like Voyager. It's a flying high gain antenna, because one of the biggest problems is I've got to be able to get the data back. I've got to be able to power it. I'm going to have some sort of a radioisotope power system to do that. People have looked at things like large nuclear electric propulsion systems. People have looked at solar sails. One of the things that we did in a NIAC study back in 2004 was to look at something where that I had a radioisotope electric propulsion system on board. Another idea. This has been looked at also at Team X at JPL. It's been looked at ESA studies. One of the things that's sort of the new kid on the block right now is the Space Launch System. The SLS Block 1B is what is being envisioned as will be operating by 2018, we'll see, to launch the Orion manned vehicle. It could give you a high C3. You can add a Jupiter gravity assist. I can actually use, also think about using Jupiter and an Olbert maneuver close to the sun, another idea, but there's increasing difficulties if that I try to do that sort of thing. But nonetheless, using this this vehicle that people are talking about within NASA's Human Exploration Division is something that could be enabling for doing this and a lot of other solar system science. We've looked at some of the performance, putting upper stages on this thing. One of the things that's been looked at is trying to get down to maybe 200 AU out in 20 years from launch. The idea here is that what one could do is to actually do the maneuver that Oberth talked about back in the 1920s, 1929, that I go out to Jupiter, I slow the spacecraft down with a reverse gravity assist, fall into the sun, and come in very, very close to the sun and use a powered maneuver there in order to greatly increase the energy with which that I could leave the solar system. One of the issues there, of course, is there's no way of actually testing that. And there's no way of actually, you're going to have a critical maneuver, which that if you fail, you're going to fail with your mission. And so some of the realities of dealing with NASA these days mean that this sort of thing gets to be very, very difficult. Also, you'd have to end up figuring out how to put a solar shade on the side of the kick stages, another very difficult thing to do that involves a lot of money. And this is one of the things we were talking about at the Keck system. But basically, again, the idea is I get down to a very small spacecraft, and I'm going to need something like the SLS Block 1B even to do this because of the amounts of energy that I actually need to be able to pull this thing off. And this just, again, gives you some idea of what the trajectory looks like. It turns out trying to do this with a maneuver close into the sun means that I spend a lot of time within the inner solar system. Now, the advantage to this over doing a direct high-energy launch out from the Earth is that potentially out at 200 AU, I'm going to be going about twice as fast because I can pick up more energy. But I actually get to 200 AU in about as much time. So again, it revolves back to how long can I actually guarantee as a requirement up front before launch that this probe might work. A lot of the pieces exist, a lot of the pieces don't. There are a lot of enabling technologies that I'm going to have to think about one way or the other. But these are all things that are actually within the grasp of what we can do in the next 5 to 10 years. These are not out of family with other things that NASA and other contractors are doing that are required for other scientific missions that are going on. Again, I can think about just using the high C3. I mean, the SLS and the upper stage for that are under development. The real question is how do I make that affordable, and who's going to pay for the launch vehicle, and how is that going to be supported? Because the Science Mission Directorate within NASA does not have money to be able to actually pay for one of these boosters. On the other hand, if the United States is going to develop these, you need to be able to build and launch about one a year in order to keep the knowledge base constant and available. And that is problematic because we probably can't afford to do a human mission once a year on the current budgets. And so this is actually a way of doing some of these science missions that you can help to keep this capability in place. We looked at using just a Delta IV Heavy. Back in the days of the Ares 5, we actually looked at trying how that you might put that together with a stack. And we're able to get some ideas about really what that you could do in a limiting sense of doing a direct ballistic launch from the Earth, whether I'm doing a Jupiter gravity assist. This is on showing the heliocentric speed. Of course, it drops very rapidly from launch on the left because I'm climbing out of the sun's gravity field. The discontinuity is what I get with a Jupiter gravity assist, and the other sloping lines is what I could get with a radioisotope power system if that I were using that to go to ion engines and gradually accelerating on outward. But again, one can at least bracket what is possible. And for just about all of these, I end up with a travel time out to 200 AU of something on the order of maybe 25 to 35 years. And it's very difficult to get anything that's going to be better than that. So at least with the SLS, there's some notional solutions that are out there that we could think about doing. And of course, our heliosphere is a key to the bigger picture. And so one of the things that NASA does is in looking at science. There's a decadal survey that is done once every 10 years. There will be another one that will be coming up here within another 5 or 6 years or so. The Congress looks at that. The Congress pays attention to what is said by the science community in that. And so currently one of our goals is to try to get this idea of an interstellar probe back into the decadal surveys so that in the decade of the 2020s, this sort of thing might actually become a reality with an appropriate funding line that we could actually launch. It turns out to go in the right direction, to get out to the interstellar medium, to go by Quasar, have the Jupiter gravity assist. The ideal launch date's about 2026. They happen about every 12 years because I have to get Jupiter back to around to the next place, bright place in the solar system. So the last time was 2014. We missed that. 2026 is the next one, and then 2038, probably plus or minus 2 years about those. So it certainly is a high scientific priority. People have talked about solar sails. I think there's some problems with those. That's a wholly different engineering and mechanical topic to talk about. But nonetheless, trying to be able to do this sort of thing with this existing technology is something that we could do. It really is a question of what we want to do. Lao Tzu, of course, said that a journey of 1,000 miles begins with a single step. This is not going to take us to the next star, but it is going to be the next step past the Voyagers, and it's something that's doable, and it's something that, again, as Mike was referring to, the fact that we end up doing things now which are going to end up needing to be done in order for things even greater to be done in the future. So it really is just a question of how and when. And so again, we're trying to get, I was talking to a lot of people this last week in Florence about this, many people in the science community that are involved with Solar Probe are also interested in this. And the Committee for Space Research, COSPAR, which is an international society that's been set up, has been around since the early 1960s, has just recently established a panel on interstellar research for being able to look at this. I'm the new chair, and I've got to get my act together about trying to get this organized. And so what we're going to be doing, my goal is to get together both scientists in the U.S. and internationally, try to get a report together, use that as input to the decadal survey process, also try to get some more interest at the European Space Agency. Of course, something like Ulysses, it would be a joint international project, is something that might be able to make this thing work. So this is not going to the next star, but it is going to the interstellar medium, and it would be the next Starship from the Earth. Thanks for your attention.